I'm Jake Bruton and welcome back to What Should I Use? I'm not going to tell you what our topic is today. I'm going to start by telling you a story, and I want to talk about my wife. Bear with me for a second. When I was building my personal house from 2018 to 2020, I'm going to tell you that I probably had somewhere in the range of 10 to 20 conversations about water filtration, about the quality of the city's water, about the quality of the drinking water that was going to happen in our house, about if we put in water filtration, would it be whole house filtration? Would it be point of use filtration? If we put in whole house water filtration, would that do anything to our fixtures? Would it make cleaning fixtures easier? Would it matter? Is it more cost effective to just do point of use? If we just did point of use, does that mean our ice isn't filtered? Do we care about whether or not our ice is filtered if our water's filtered? All these long conversations, and then we ended up moving into a house without water filtration because we couldn't figure out where to put it or what we wanted to use. And this was a very important topic for my wife. Me, not so much, because I know that the water quality in our municipality is deemed to be fairly safe and okay. But this conversation was really important to her. And I just kept thinking, this is a conversation that you hear in society nonstop. What kind of water are you putting in your body? Does it need to be filtered? This is a huge industry. And very few conversations happen in the same way about the air we breathe. Think about how much of the day you spend actually drinking something, putting water into your body, and then think about how long out of the day you spend breathing, because even while you're asleep, you're breathing. So the air we breathe is really, really important, and it's constant throughout the entire day, but the water we drink is very small and only part of the day. So today's topic is going to be the V in HVAC, ventilation. Let's talk about that thing that we do all day long, that air we breathe, that air inside of our building. Today's What Should I Use? Ventilation. Let's do it now. What Should I Use? A Build Original series with me, Jake Bruton. Today's episode of What Should I Use is sponsored by 475 High Performance Building Supply. Okay, so when we talk ventilation, I want to start by talking about my first experience with the V side of things in the way of makeup air, because you can see behind me we have an ERV, and we'll talk a little bit about that in a minute. Late 90s, the first time that I experienced any sort of makeup air, quote unquote makeup air, was on a project that I was actually the project manager on a new construction home. And on the plans was labeled makeup air, and to the mechanical room of this custom home that our firm was building was an 8-inch duct that was cut from the outside of the building to the inside of the building. No damper, no filter, no mechanical conditioning or anything like that. It literally was just an 8-inch hole in the side of the building in climate zone 4A from the outside to the mechanical room. And they were using this makeup air as air to feed the combustion appliances, as in the water heater and the furnace, and so that the building got a little bit of air. And I questioned this, and our HVAC contractor at the time said, this is how we do it. And even at that point in my career, when I was very young, and I thought, how can this possibly be good for the house when it's cold outside, like it was at the time that they were drilling a hole in the side of my building? We're just letting freezing cold air into the building. How are we supposed to compensate for this? And then in the spring, it's going to be humid. And then in the summer, it's going to be hot and humid. And then the only time of the year that it's really not going to matter is when it's 75 degrees and not humid in the fall. The whole rest of the year, we don't want that air coming in here, except for we have to have it for the combustion appliances in this room. And I really didn't understand why that was the solution. But at that point in my career, I didn't know enough to know what the other solution might be. So I literally just nodded my head and said, well, if that's the way we do it, that's the way we do it. It didn't take long for us to start exploring other ideas, dampers, direct vent appliances, things like that. But that was like my first introduction, and I already understood that's a challenge. Why are we doing it that way? So that doesn't happen much anymore. When we start looking at what's allowable by code, when it comes to ventilation, we're going to talk about exhaust only, supply only, and then we're going to talk about balanced. So I use the word balanced in the third setting because the first two are unbalanced. If you've ever looked at a scale at the Lady of Justice statutes, unbalanced is probably not the way you want to go. So let's just start by talking about those ways, and we'll talk about why I don't prefer that method. So exhaust only. Yes, we're exhausting the things we don't want in the building. That would be like a range hood, a bath fan, or a dryer vent. We're getting rid of moist, stinky, contaminated, potentially air. We're taking that air, we're moving it outside of the building. That's a good thing. However, your building is not a completely sealed environment. When you pull air out of it, it has to replenish that air from somewhere. Meaning, if I take, let's just keep it simple, 100 cubic feet of air and move it from inside the building and I put it outside, the building will not just operate at a 100 cubic foot of air deficit, it will replenish that air from somewhere else. Meaning it will leak from weather stripping on windows or doors or sill plates or poorly sealed electrical outlets and exterior walls. That air will replace itself from somewhere else in a fashion that you do not have control over. In other words, that air is unfiltered and untempered, meaning the air you're bringing in is just outside air. So you cannot guarantee to your clients that that air is going to be fresh. Now, if it were just 100 cubic feet of air, that probably wouldn't be that big of a deal. In a 3,000 square foot house or a 2,600 square foot house that's 26,000 cubic feet of air, that wouldn't be a big deal. But if you had a range hood that was even operating at 400 CFM, that's 400 cubic feet of air per minute. If you're cooking steaks for 10 people and that takes 20 minutes to do or 30 minutes to do, that is an incredible amount of air. Now you have exhausted a ton of air and you've brought quite a bit in. And if there's a huge delta between inside and out, between temperature or humidity, those would be huge issues for your building to try to overcome. Or if there are lots of pollutants outside, say they're repaving the street, now you have all that asphalt smell inside the building. Now you have contaminants from outside. Now you have pollen or particulate matter that you didn't want inside the building that's just leaked in because you don't have control over how it's coming inside the building. The same thing happens with supply only. If you are pressurizing the building, you have to make sure that you are filtering or tempering, and most of those systems just bring it in, and they have a tendency to try to plumb it in to the furnace. And if you're going to plumb that into the air handler, most, not all, but most HVAC crews will plumb a fan into the return side of the air handler so that it will run through the filter before it goes into the air handler. Therefore, you temper it, and then it will run through the air handler, and then it will be conditioned. That works amazingly well as long as the system, the air handler in this case, is actually running. If the system's turned off, the air that's coming in, that makeup air, could potentially backdraft and just run the path of least resistance, backdrafting into the house, and therefore you now have air that's dumped into your ductwork and filtered into the house without being tempered or without being filtered. Obviously, there are mechanical ways around that, but now you're pushing air in, and that air that's not being compensated for, say we're bringing 100 CFM in, now we have to push that air out because it's not just going to balloon. The house isn't just going to grow. That air is now leaking in a way that you don't have control over. So where is it leaking? It's leaking in the same places that we would be leaking in if we were just depressurizing in. We don't have control over that. That could cause problems. We could have warm, moist air or inside the building, and it could be causing condensation in our walls. It could be causing moisture to get into the wall cavities because it's leaking through electrical outlets and it's finding a condensing surface because we're in a cold climate, or any other number of reasons that it's just uncontrolled and that causes problems. The whole point of us building a building is control. If we didn't want control, we would just live outside. And we build buildings so that we have control. So let's look at the specific code in the IRC 2021. It is M1505.4.1. M stands for mechanical in this case. It's system design. The whole house ventilation system shall consist of one or more supply or exhaust fans, that's the pressurized or depressurized, or a combination of such, and associated ducts and controls. Local exhaust or supply fans are permitted. That means you could do bath fans or exhaust hoods, or you could do room by room to serve as such a system. Outdoor air ducts connected to the return side of an air handler shall be considered as providing supply ventilation. So that's what I was talking about a minute ago with supply only. You can duct into the return side of things. So code allows for a mixed bag of what we're doing here. Basically, they're saying, do what you want. There's a whole bunch of options in that one paragraph, and that paragraph is like 4 sentences, and it kind of covers do whatever the heck you want. I don't like the depressurize only or pressurize only because there's so much that's out of our hands in that point. The other side of this is there's also mechanical ventilation standard 1503.6, which is makeup air. So let's look at that real quick before we move on. And it says makeup air required, where one or more gas, liquid, or solid fuel burning appliance that is neither direct vent nor uses mechanical draft venting system is located within the dwelling's unit air barrier. Each exhaust system capable of exhausting in excess of 400 cubic feet per minute shall be mechanical or passively provided with makeup air at a rate approximately equal to the exhaust air rate. Okay, so there's a lot to unpack in this one because this is one that comes up quite often in the custom home side of things. Number one, if you have a fuel burning appliance that is your cooktop, and that's gas, liquid, or solid fuel, so I'm not sure what solid fuel would be in that state. Coal burning, maybe, I guess. If you have something that's burning an actual fuel that you're cooking on, and you have a hood over top of it that is more than 400 CFM, which if you've shopped for a range hood, a lot of them are, you're going to have to provide mechanical makeup air. Meaning, you can't just depressurize the heck out of your house, you have to put some air back in. So the code's recognizing here that just depressurizing causes problems, so don't do it. The other thing is at a rate equal to the exhaust air rate. That's super important. If you are mechanically pushing air out of the house with a fan, as in the exhaust hood, and then you just provide a damper, even if the damper is the same diameter as the exhaust hood, that damper is not going to provide the same amount of air as the exhaust hood that's powered. Your damper needs a fan at about the same rate as the exhaust hood because the damper and pipe just doesn't have the same power that the powered exhaust hood is. And a lot of folks don't understand that one side being powered and the other side not, they're not going to draw the same amount of air. We've done testing on systems that we put in thinking that we were going to get that, and we've proven that it just flat out doesn't work. So we recommend to our clients, when you're providing makeup air in a situation like that, buy the same fan motor from the same manufacturer. There are companies out there that make range hoods that then make the makeup air to go with them as well. The other thing to note is the code only talks about for fuel burning. So if you're moving to things like induction here, it's not important that you do this, but I don't see a reason why you're putting in a range hood that's over 400 CFM, for instance, and not still abiding by the idea that you don't want to provide that makeup air. It makes perfect sense that you still would want to do that. Now I want us to reference the table that provides continuous whole house mechanical ventilation rates, and that is table M1505.4.3.1. And this is a super simple table. It's a broad reaching, this is a hammer to drive a nail. It's not super accurate. It's not to the decimal point, but it's a very easy one to follow. So on the left, we have the dwelling unit floor area. On the right, we have number of bedrooms. And the reason number of bedrooms is important in this case is because the code uses number of bedrooms to make assumptions about how many people are staying there. So what they do is they assume a happy household where there are 2 people living in the primary suite and then a child in every other room. So what they do is they take number of bedrooms and then they just add 1 more person than the number of bedrooms. So if you had a 3-bedroom house, that's 4 people, 2 people in the primary and then 1 in each of the other bedrooms. And then they take the square footage and they assume volumes. So they make an assumption based on the cubic volume of the house based off of, I think they assume that it's like a 9-foot ceiling or something like that. So if we were to take a, say, 2,000 square foot house or something like that and a 3-bedroom house at 2,000 square feet, you can see that the code would recommend that we have 60 CFM worth of ventilation if we were using this chart. That is a fairly simple thing to do. This chart is also basically ASHRAE 62.2. ASHRAE is the American Society of Heating, Refrigeration, and Air Conditioning Engineers. I know, some of the coolest people on the planet. But the ASHRAE 62.2 standard is 90 pages. I'm going to save you the 90-page read. I have read all the way through it. I'm not going to pretend that I understand absolutely everything in it. What I do understand is the overlap in this section of the code from this table to that section for the residential single-family part of the code. And their calculation is close, but it's not the exact same number because their calculation is a little more refined. And their calculation is like this. It's take the number of people times 7.5 CFM, use the number of bedrooms plus 1. So it's the same sort of number of people as bedrooms plus 1. Take 1% of the square foot of the house and add it to the number from step 1. So for our example, a 3-bedroom, 2,500 square foot house, it's 4 because 3 plus 1. Times 7.5, that's 30 CFM. So 2,500 times 1%, that's 25 CFM. So 30 CFM plus 25 CFM equals 75 CFM. So ASHRAE's calculation gets us to 75 CFM, where the code table got us to 60 CFM. So you can see that there's a little difference there. They're close, 15 CFM when we're talking about a potentially, what would that be, close to 25,000 cubic foot building. That's not a huge difference in air, but it is a mechanically different amount of air that you're bringing in. So you can see that this is a broad stroke that we're painting here with this big brush on what are we bringing in, what are we not bringing in. The lesson here probably is that because this is so broad, you probably should rely on your HVAC professional to tell you exactly what it is, and or you should design your system to meet whichever one of these gives you the higher number, and then commission your system to meet the needs of your clients. Now let's talk about the system behind me and an ERV, and what do we get from an ERV or an HRV. So let's talk in general first. An ERV is an energy recovery ventilator. We're talking balanced ventilation here. We have the ability to bring air in from the outside, bring it through the device, and put air into the building. We have the ability to bring air from inside the building in the places that we don't want the air anymore. Bathrooms, kitchens, places like that are stinky, smelly, contaminated, whatever it might be. Bring it through the device and eject it to the outdoors. So we have a mixing box where the air doesn't actually mix. It runs through a central core inside the box. It runs through a membrane where the air doesn't actually touch. It just runs very close to each other so that the thermal energy can transfer from one stream of air to the other, meaning we get to temper the air without using any actual energy. All we're using is the fan energy to move the air. Okay, now that we know what the code says, let's talk about how we get to balanced ventilation. There are different ways to get there, but I think one of the simplest ways to get there is a system like the FLAIR series from Brink. It's an ERV. Let's talk the differences between ERVs and HRVs and what we might use them for. This is a balanced ventilation system. We are pulling air from outside. We are pulling air from inside the building. We are ejecting them. They are crossing paths. Let's talk about how this works. So first and foremost, just on the most basic level, I think it's important that we clear something up. The difference between an ERV and an HRV is that an HRV moves heat and an ERV moves heat and moisture, but it is important that we understand that an ERV is not dehumidifying. It can only create closer to equilibrium conditions. So it is not actively dehumidifying anything. What we have is we have a core in the inside of this unit that allows us to push air through the unit from outside to the inside, from the inside to the outside. The streams cross each other without actually touching. They just pass by each other in a way that they can share their thermal energy, or in the case of an ERV, their moisture content. Everything, according to Newton's second law of thermodynamics, wants to be closer to the thing that it was. Everything goes from more to less. Heat goes from hot to cold, or hot to less hot, I should say. And by doing so, the membrane in the core of the unit and the scale of the core, the longer the air can pass by each other, the more efficient the unit, like this. We have the ability to steal the temperature off of that. So the cold air, say, from outside will warm because the warm air from inside the building is passing next to it, or vice versa. And so you have air coming in from outside that gets tempered. The other thing that these units do is that they have filters. There are filters to stop things from coming in from outside, things that you don't want, like pollen or PM 2.5. You can get HEPA filters so that you get very clean air coming in from outside, because without filtering it, you're just getting outside air. And then they also have filters to bring from the inside air to stop anything that might be from in your house from contaminating the unit and causing damage to the unit as well. So when you have a unit like this, you are now completely in control of the air that's coming into the house. You are tempering it, you are filtering it, and you have control over the speed or the volume of air that's coming into your house. So you have that ASHRAE number, or you have that code number of the amount of air that needs to come into the house. You have the ability to boost it if you have an event that causes the air to be needing to be exchanged at a greater rate. And now you have just an added layer of control. So what about a premium ERV like the Brink FLAIR series makes it worth investing in something that is a premium product rather than just a run-of-the-mill box ERV? Let's run through some of the features that I think are the important thing that makes it be one of the things that our company uses. Let's start first with filtration. We've talked about filtration. That's one of the big aspects of control here. Filtration is the thing that makes indoor air quality super important. It gives you the ability to know that that air is clean. We have the ability to pre-filter. We have the ability to add HEPA filtration to this. We have the ability to ensure that the air that's coming into our building through this unit has been filtered. The HEPA is a huge asset. There are a lot of ERVs that the internal fans, the motors, are not powerful enough to add HEPA to, and that is one of the things that is super important with this unit. It also is, or should be noted, that some of the cores are not able to have HEPA added to them, even if the fans were powerful enough. While we're talking about core, the core is the next big asset for this. Both the HRV and the ERV core, they are elongated. They have a larger surface area. That allows there to be a lower operating pressure, and that gives us a higher thermal efficiency. It gives us longer period of dwell time for the air in it. That's how we get our higher efficiency, and it just makes the unit operate and use less energy. So they're going to say like it sips energy compared to some other units. So when we're talking about adding a system to our building that 10, 15, 20 years ago we wouldn't have had in our building, we're going to have to make an argument to the client that like, yes, we have now built a house that is so tight that we have to spend money on a unit and spend energy money on to operate that unit. We should be buying a unit that is going to cost very little to run. And the more efficient we can buy, the better off we're going to be in making that argument with our client. And the core being that much bigger, that more elongated unit, and allowing longer dwell time for the air in the core, that's going to help us with our efficiency, both in the HRV style and the ERV style. While we're on the topic of the efficiency, we should talk about the fans inside the unit. They are high efficiency EC fans, electronically controlled fans, and they have a vane anemometer at the end of them. That means that the flow is very constant, it's ultra precise, and it's very easy for the unit to measure and balance. That way we can balance what's coming and going. We have the ability with the electronic controls, the digital controls on the unit, to balance the unit so that we could even slightly pressurize the house. That's something that our firm does normally. If we operate under a slight pressure, we're forcing out a little bit. That can help with infiltration of things like radon. It can keep outdoor air from filtering into the house. I would rather leak a little bit than leak out a little bit rather than leak in a little bit. So I'm able to do that with these ultra precise fans and good control systems. The other aspect here that a lot of units don't have, because the brains on this unit are so intelligent, we also have a 100% bypass. We can completely close off when conditions are not right for the system to be running, and we can just filter and send the air back into the building. That is key for it is not the right time to be running the unit, and the unit can recognize that on its own. That 100% bypass is a pretty unique feature to the FLAIR series. One of the last key features of the unit is it also comes built in with a preheater, meaning if the air coming in is cold enough that we might get frost in the core or the unit, it has just a little bit of an ability to kick on and heat up that air. It's not something that runs all the time. It's sensor driven, it's intelligent, it takes care of itself. It's not something you have to turn on. The unit is taking care of itself, and it will heat up that air just enough so that we don't get any frost in the core. That would cause problems, so we just don't want that to happen. It's not something you have to order extra, it's built into the unit. So the system is really set up to kind of take care of itself, to be worry-free. All you have to do is conduct your regular maintenance on it, just like you would the rest of your HVAC system. And now we have a system in place to ensure that we have filtered, tempered, clean air coming into the house. And that's what we're shooting for, right? Like that conversation that I had with my wife where we're talking about we want clean water, we want clean air the same way. We want to have control over it. We want to know for sure that the air that's coming into our building is not contaminated, that it's a temperature that we're going to be happy with, and that we're doing it in a way that we can ensure the results are manageable and that they're what we want. And with systems like an ERV from a reputable manufacturer, that's the best thing that we can do. We know what the code's asking us to do. We have to have turnover once we get to a certain point. That 3 ACH 50 number, we need to be providing mechanical ventilation to our clients. And at that point, just exhausting is bad, just bringing in is bad. It's worth it to provide balanced ventilation because that's optimal control. As the builder, as the professional sitting at the table, you need to be providing control to your clients, because if you can't provide control to the clients, what are you providing? If you're providing a building that doesn't have control, you may as well be asking your clients to be living outside. You're not providing what you're selling them. This is one of the things that I would say is the most important to your building. This is part of the comfort package. This is part of what you should be selling to your clients. Sell on comfort, sell on control. Think about the V in HVAC. when you have your next sales meeting with your clients. Till next time, thanks for watching What Should I Use?